Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. Ramadan Kareem to all of you and to your families. Um, our topic today will be the nuclear magnetic resonance. In the lecture, I will be talking about a little bit of the history about the Enema, and then I will discuss the need for the Enema, why we need the Enema, and what is the physics behind the Enema and the logging tools and the different measurements which we can record from the logging tool, the analysis, the interpretation, and the application. And lastly, we will see some examples of the application of the NMR and the tools which have been or which are manufactured by different oil companies like Schlumberger and like Halliburton and Baker Hughes. So if we go to the history of the NMR, actually the technique or the physics of the NMR was introduced since the 1940s, but was not applied and was not involved in the oil industry until the 1990s, exactly in the 1992. So it's a kind of new technique and new tool in oil industry which came to overcome the problems and to solve the issues which have been found and have been faced and encountered in the conventional logging tools like the porosity and like the resistivity, because we have seen already that they are too much affected by the lithology and by the matrix. Changing the matrix will change the quantities or the properties which we can extract from those logging tools, like the density and like the sonic log and like the NMR. We have seen that they are too much affected by the lithology. So the NMR came to provide a porosity measurement and fluid type measurement which will not be dependent on the matrix. So if we come to the physics behind the NMR, it's not that difficult. Actually, the quantum mechanics has already proved that the atomic nuclei, they have a magnetic moment which makes them behave like magnets. This nuclear magnetic moment is actually caused by different rotation movements of the nucleons. And this magnetic moment will enable the nucleus to interact with any externally applied magnetic field, and this will produce a measurable signal. And this is what we will be measuring, this signal. So the frequency of the movement or the precision depends actually on the magnetic field and on the nature of the nucleus, because different nucleus, it means different frequency. This frequency is called the Larmor frequency and is found to be in the range of radio frequency. So in the case of pulse radiation, or if we radiate pulse or we emit an energy or a pulse of energy with the same frequency of precision, the protons actually will absorb the energy of the pulse as it is applied by this field, and then the protons, they will radiate this energy after we stop or after we end this pulse or this field. So we say that they resonate, and the process is called resonance. If we come to the hydrogen atom, the hydrogen protons actually in nature, they are already in continuous precision movement with relatively large magnetic moment compared to many other elements. The hydrogen, as we know, is very abundant, is very much present in both water and hydrocarbons, which are saturating the pore space of the rocks. When no external magnetic field is present, the hydrogen protons, they will rotate randomly and there will be no measurable signal. But when they will be aligned uh, as a result of the presence of an external magnetic field, there will there will be a measurable signal which will come and will be the result of this alignment. So now let's see the magnetic resonance process and steps. The principle of the nuclear magnetic resonance relies on the response of the hydrogen nuclei that are under the influence of the magnetic field. So there must be a magnetic field there in order to have the alignment and in order to have any measurable signal. So we have a couple of steps in order to execute or to run or to implement the process of resonance. So in the beginning, we will try to align all the protons motion or rotation direction, and we will try to put them all in the same direction with the help of the first magnetic field. Then we will try to execute or we will try to apply another field. This field or this magnetic field will try to deviate them and to make them get away from the first orientation. And then lastly, we will try to remove the electromagnetic pulse, and then we will measure the resulting echoes produced by the protons. The polarization time, actually the protons, since we start or we launch the the magnetic field in order to make them all aligned, this will make some time until all the protons will be aligned. And as we have mentioned, once they are all aligned, we will have a maximum of measurable signal or maximum of magnitude of this signal. And this can be expressed exponentially or in an exponential form. So as we see here, we have the polarization curve. We see that the signal will increase exponentially until we will reach plateau or a maximum. And then after the polarization, as we have seen, we will apply another field. This field will try to deviate them or make them deviate or get away from this polarization direction. And this is what we call the tipping. By applying a pulse tipping, so this will be done a number of times, and the experience has proven that once we are applying this process a number of times, we will see a decrease in amplitude. This amplitude, which we have seen in the beginning here, or the maximum amplitude, which can be reached by the full alignment of all the protons, actually will get low and low every polarization process or every NMR process. So, and this will provide us also another exponential curve, but this time it will be a decay curve where the maximum amplitude or the first maximum amplitude will never be achieved again. So, and then so from this exponential decay, we have another time constant, T2. We will call it from now on the relaxation time. This relaxation time is actually a composite of a number of individual fluid decays in the formations. So the initial signal amplitude is proportional actually to the number of hydrogen nuclei which are in the fluid which is saturating the rock, and this will give actually a porosity measurement or a good measurement of the porosity which will be independent from the lithology. The relaxation times depend also on the pore size. So it has been found that large pores, they will allow long relaxation times and contain producible fluids. However, the small pores, they will shorten the relaxation time and they contain clay bound and capillary bound water. So now the NMR logging tools. In the NMR logging tools, we are applying exactly the process or the previous process which we have seen with the 3 steps. So in the beginning, we will run or we will apply a magnetic field. This magnetic field will try to align all the protons and to make them rotate in the same direction. And then we will have um, a tilting pulse. This tilting pulse will try to deviate the movement of the protons and to make them deviate from the first polarization direction. And then we will remove the magnetic field, and then we will measure the signal which can be as a result of this process. We will do that several times until we will have an exponential decaying curve. This curve, or this exponentially decaying curve, will provide us with the T2, and the polarization curve will give us actually the T1. And both T1 and T2 will help us to have and to extract information about the pore size and fluid types in the rocks. So now we will define the cutoffs of the T2 distribution or the relaxation time distribution. As I have mentioned already, from the exponential decay, we can have the T2. So the T2 is nothing but is a constant time which can be extracted from the exponential formula of this decay or decaying curve. And then if we try to plot the T2 along our interval from the decay or from the exponentially decaying curve, we will have a distribution of T2 in this form. So in the NMR, what do we have? Or in the NMR analysis, what do we have? Usually, we try to use this distribution of T2 in order to extract the fluid types and the pore types and or the pore size, because this distribution of the relaxation time is indirectly measurement of how much time the protons will take time in order to get relaxed. So if we put some T2 cutoffs, they will help us really to discriminate between the pore size and, as we will see later on, the fluid types. Why? Because different pore size, they will contain different types of fluids. As we see here, the when we have very small T2, so it means we will have clay bound water. In the little bit larger T2, we will have capillary bound water. But when the T2 or the relaxation time will be large, so here we will have producible fluid, because these kind of producible fluids, they will be found in large pore size. So this is an example of the NMR logs, which can be recorded at the borehole or at the well location using the NMR logging tool. So as we see here, we have relaxation time curves here, or relaxation time T2 distribution. We see here, for example, that we have only small T2 or very small T2. So it means we are in the first range where we have only capillary or clay bound water, and we don't have any movable um, fluids, because we don't have any relaxation time or large relaxation time. So, and this is an indication that we have only small pores or small pore size which are mostly in shale. In sandstone, we see that we have a large relaxation time, which is an indication of large pore size. So I hope this is clear. So as I mentioned, the T2 distribution is a direct way or a direct access to the pore size, and from the pore size we can have an idea about the fluid type. Because, for example, if we see that we have a movable, or we have a large relaxation time, this is an indication of presence of free fluid. But this free fluid, it can be water or it can be hydrocarbons. So here we will need to use, for example, the resistivity in order to confirm that here we have hydrocarbons and not only water. So this is one option. The second option, we can also use the T1, because as we will see, the T1 and T2 themselves, if we take them quantitatively, they will be kind of direct indication of fluid type. So now the porosity and permeability from the enema. In theory, we know that the permeability will increase with the pore size, and the amount with the amount also of the effective porosity. If we have a large effective porosity, it means we will have large permeability. So the NMR can be used to estimate the total and the effective porosity. We call it the TCMR by the integration of the BVI and the BVM. The larger the pores are, and the more interconnected the pore network is, the more capable reservoir to transmit the fluid. It means the large is the permeability. Quantitatively, and in terms of equations, we have different equations to estimate the permeability. The first one is according to the free fluid model. It uses the relative proportion of the free fluid to the capillary bound fluid with an effective pore. So both of the measurement we already have from the NMR, in addition to the porosity from the NMR. So we have the three parameters, these three parameters, plus this C, which is constant, depending on the formation. We can have a good estimate about the NMR permeability. We have another formula to estimate the permeability. This other formula or other expression is actually using the porosity of the NMR and also times the square of the geometric mean of the T2 distribution. So we are using the relaxation time here in order to estimate and in order to calculate the permeability. So now in terms of fluid types, also it has been found that different fluid types, they have different polarization time and they have different relaxation time. So the brine has or water or salt water, it has polarization time which is smaller than the oil, and the oil has polarization time which is smaller than the gas. But in terms of relaxation time is different. The gas has very small relaxation time compared to the brine and compared to the oil, but there might be some overlap. So lastly, here we have some examples where we show the NMR uses in real field analysis, real data analysis, and real data interpretation. So this is a similar example to the one which we have seen previously. So here we have the NMR log, and here this is the T2 distribution. So the T2 distribution is showing where do we have large pore size, and with the help of the saturation and with the help of the other logs like the porosity and like the resistivity. So this is the porosities. So we can estimate and we can find where what type of fluid we have, and with the help of the NMR, we see where do we have a large pore size where we can find movable or free fluid type. This is also another example from Northwest Australia. In this example, we have also different types of well logs. These we have this log is, for example, is the NMR or the T2 distribution. We have also the density and the neutron porosity. We see the overlaps, and we see here the crossover, and we see the separation between the logs where we have a good amount of gas. The resistivity is showing where do we have maximum resistivity in the presence of hydrocarbons, or which is caused by the hydrocarbons. So now the Enema will show us that in the reservoir level we have some large pore. These large pores, they contain the free fluid, or this gas which we have seen using the density and using the NMR log. Lastly, there are different types of tools available to measure the NMR. Some examples of the NMR tools, we have we have two by Schlumberger. We have the combinable magnetic resonance tool, the CMR. We have the magnetic resonance fluid characterization, the MRF. And we have another one by Baker Hughes. It's called the Magnetic Resonance Explorer. And we have the Halliburton magnetic or NMR tool, which is called the Magnetic Resonance Imaging Logging. So all these NMR tools, they are providing also almost the same thing. They are providing the pore size, they are providing the relaxation time, polarization time. So they are doing the same job, which is using the NMR principle in order to have access to the porosity of the rocks and the fluid types. I hope this is clear, and I hope the slides are well explained. You can go to the papers which I'm giving you in the Moodle. So there are some papers which will help you to maybe broaden your spectrum or your learning or your understanding about the NMR. There are also some videos which are available on the YouTube and on the Moodle. They will help you also to understand the NMR. So that's all from my side. Thank you very much, and see you in the next coming lecture.